Hello everybody. In this video, I want to talk about something that is relevant to one of my previous videos, and that is calculating the phase difference between two signals. So if I have one signal and another signal, let me show you what I mean. So here, let's say I have a signal x1 and I have a signal x2 and they are given by some numbers, right? Just numerical signals. How do I know how much is the phase difference or phase lag or phase shift between them, right? Or the time lag between them? Well, and the reason for that is in one of my previous videos on vibrations, when I wanted to calculate the phase shift between these two signals, right? So I have this response of the system signal and the input of the system signal. The phase shift difference between them is this phi, and getting magnitude of the output is not hard. I just looked at the steady state, divided the max minus mean by 2. I got the amplitude. But the phase shift between them, I wanted to know how to get the phase shift, right? And so I found two good ways to get the phase shift between two numerical signals. One is called Hilbert transform. The other one is the cross correlation. So let's look at these two methods briefly. And I don't want to teach exactly all the Hilbert transform, what is it, and go over several examples. Just want to tell you what Hilbert transform is, what does it do, and how it can help us find the phase shift between the signals, and then of course the cross correlation. So what is the Hilbert transform? It's a mathematical transform. It's an operation that you apply to a real value signal, and the result of that is a complex signal. Okay? Now, the real part of that complex signal is your actual signal, the one that you gave to it, and the complex portion of it is a signal that has a phase difference of 90 degrees with respect to the real one. So this x hat part is phase shifted version of x. By how much? By 90 degrees. Okay? So you give a 90-degree phase shift to x and generate signal x hat. And now you can, of course, write it as in polar format too, where a is the magnitude of the signal and phi is the phase of the signal. Okay, so if you write it this way, what's good about it is if you get the magnitude of the signal, the magnitude of it is what we call the instantaneous amplitude of the signal. But what I care about in this case is to find the angle of it, which is arctangent of x hat over x. That is the instantaneous phase of the signal. Okay? Even if you want to find the frequency, like let's say this x is a harmonic signal, like a sine or cosine, if you want to find the instantaneous frequency, you can take time derivative of that phi, and you can even get instantaneous frequency of the signal. So what's the use of that now? How does it relate to what I want to do? Well, so I have X signal and I have Y signal, or let's say in the case of vibrations, I have the F signal, right? And I pass both of these to Hilbert transform. And using this formula here, once I have the Hilbert signal, right, the complex signal, which we also call it analytic signal, I can find the phase of each one. So I find phase of X, and then I find phase, instantaneous phase of F. And if I want this phase shift between them, all I need is to subtract these two. Okay, so you see, it is really great in terms of what it does. The good thing is, the best thing about it is, as I said, it gives you instantaneous phase, and that's what I want. So, first thing is, what is Hilbert transform? Then I said that it makes an analytic signal. So what is analytic signal? Analytic signal is basically a complex value signal that the real part of it is your actual signal and the imaginary part of it is the Hilbert transform version of the signal. When you form a signal like that, we call it an analytic signal, which is exactly what we are doing here. Now, what is Hilbert transform? Hilbert transform the way that it generates this 90-degree shifted, phase shifted version of the signal, the way that it does it is basically by an integral here. And this integral is actually, if you look at it, it is a convolution. It's a type of convolution between what? Between your signal itself and then what? The signal, basically 1 over pi t. Okay, the 1 over t, you can see it here, and this is the pi. So you convolve your signal with another signal, 1 over pi t, and this is, of course, t minus, because you remember convolution, right? Convolution of signal, let's say, x and y, if you remember, that was the integral of x of tau, right? And then y of t minus tau. And then d tau. And then this tau can go from some number to another number, right? So that is the convolution of two signals. So you exactly see that this is the convolution of my signal x with this kind of hyperbolic signal. And when you do that and you integrate and calculate it, it is going to give you a 90-degree phase shifted signal, which we call it a quadrature signal. So a quadrature signal is basically exactly a 90-degree phase shifted signal. So it gives you that. Now here in this integral, in this convolution, there is another thing, PV, and that is called the principal value or Cauchy principal value of the integral. And what is that exactly? So this is a way that you can handle integrals that have singularities in them, and handle singularities improper, we call integrals. So again, I don't want to get into that. I don't want to necessarily solve an example for you right now on this, how to do it for a specific signal. But again, this PV is a method for handling improper integrals that have singularities in them. And this is just a formula for it. So my goal is not to go through that formula. But if you apply that, it is going to give you x hat. And if you combine x hat and x by making x hat the complex part of your signal, now you have the Hilbert transform version, the analytic signal, and then the arctangent of imaginary over real part is the instantaneous phase that you want. So all you need is a function that performs the Hilbert transform. And in MATLAB, there is a Hilbert function that performs this integral and everything for you. So again, we're going to use the code directly here. So what we do is we pass both of my signals, x and f in this case. I'm going to pass them to Hilbert transform. I'm going to extract their phases, and then I'm going to calculate the difference between them, and that is exactly the phase difference. And since it does it at each time point, so for each time it calculates a phase, right? So if I go back here to this picture, let's see here. So let's say at time of 10, it calculates one phase difference. At 9.5, it calculates one. At 9, at all of these data points, it calculates one phase difference. So if you want something stable, first of all, you might just want to look at the last part of the signal, where the signal is stable, and then when it gets you all of these numbers, it's a good idea to take an average or a median of all of them to get a more robust reading of the phase difference. So you pass this to a median or an average function, and that is gonna basically give you a stable estimation. So in MATLAB, if I want to show you how it is done in MATLAB, here is the code for it. So here I created t between 0 to 1 with 1000 data, and I made two signals. One is 2 pi ft, where f is 10 hertz. The other one is the same signal, but with a phase difference of 30 degrees, or pi over 6. Now here, originally it was 45, but I changed it. So let me just get rid of this portion, because I want you to change it to any number that you want. Then in MATLAB, there is the command Hilbert. It directly gives you the Hilbert version of the signal or transform of the signal, so you get them. And then you get the phase of them. Because they are complex numbers, you pass them to the command angle. That will give you the phase. You take the difference, and then you take the average of the difference to get a good estimate. And here I convert it to degrees, because that's in radians. Convert it to degrees, and then I show it as the title of my plot. So if you look at the plot that I have here, basically the first plot is the two signals. The second plot is the t versus the phase difference. As I said, this phase difference is a vector. For each time point you have a phase difference. Okay, so it shows you the phase difference calculated for different time points. And then this average value, it is going to show it as the title of the plot. So you're going to see this, look. So you see that the phase difference is not constant as your signal goes from 0 to 1. Now the signals here are stable. Okay, there is no transient response, so I can use the whole length of the signal. But if my signal has some transient response, it's a good idea to only look at the last portion of the signal. But you see that my phase difference is anywhere from like 32 degrees to a little bit below 30 degrees. So it's not perfectly constant, although it's kind of flat around 30 degrees. And if you take average of these values, it says that the phase difference average that it calculated is 30.02 degrees, which is very, very, very close to pi over 6. Okay, so it did a very great job. And it could find them just by doing Hilbert transform. Now here, if you look at x1 is a real data signal, but if you look at x1 Hilbert, right, you see that they are all complex numbers, as you can see. Okay, so it does calculate the Hilbert transform numerically. One other thing I need to mention is this command unwrap. What is unwrap here that I used? Unwrap is one powerful command in MATLAB that corrects phase discontinuities when the phase jumps. Because you are using an arctangent function really here, and arctangents can jump, right? You're not really using arctangent 2. And so the arctangent values could jump between negative pi and positive pi. So to correct for that and not give you a discontinuous plot and give you a continuous nice plot like this without jumping between negative and positive numbers, you can use the command unwrap to correct for those discontinuities. Okay, so this is the built-in function that gives you the nice result. So this is using Hilbert transform. Now, one thing I need to mention about the Hilbert transform, you might say, why didn't you use Fourier transform, right? Well, you know, with Fourier transform, when you pass a real signal to it, I can see what frequencies are available in the signal. I can see their magnitudes, I can see their phases, and so on. So I might be able to get something from the Fourier transform of the two signals if you compare them, their phases. That's right. The only thing is Fourier transform basically does it for entire signal. So when you pass the entire signal to it, all it gives you is a frequency plot used for all time points. But this Hilbert transform, it does it for each and every one of the points. So it calculates the phase or magnitude or frequency instantaneously, not for the entire data. And this is really good if your signal is non-stationary. If your phi, omega, or A does change over time, this guy can capture that. Like the transient response that you had in vibrations, if the phase difference between the signals is changing, this guy can catch that. Okay, and it can give you a smooth and continuous phase estimate. And it works really great when the signals are noisy. Okay, if the signals are noisy, this still can give you a robust estimate. While the other methods, including cross-correlation, if your signal X is noisy, it's not going to do a great job. And Fourier is definitely going to be messed up because, of course, you are introducing lots of extra frequencies in your Fourier plot. So for the signals that are not perfect, the signals that are not periodic necessarily, and the signals that are not stationary, Hilbert transform can give you a very, very great estimate. The second method, as I said, is cross correlation. So you pass signal X, you pass a time-shifted version of signal Y, and you integrate the product over the entire time range. That is the cross correlation between signal X and Y for a time delay of tau. Okay, good. Now, this value, if you plot this R versus tau, of course, if two signals have a time delay between them, I mean, you get different numbers for the time that is the actual time delay between the signals, right? For that value, this cross correlation will be some maximum, because exactly by that delay, you shift one of the signals so it falls exactly on the top of the other one. So this is kind of like something signal squared. So you get the maximum overlap between the two signals, ideally perfectly 100% overlap if you calculate this correctly. And in discrete signals, this integral is going to be replaced by sigma. By the way, you see that the limits here for the time or the n, the number, the sample number, is going from negative infinity to infinity. This is assuming that the two signals are infinite signals. In my case, the X and Y signal that I have generated, they have a length of 1 to 1000. So this guy is going to have limits, and it's not going to be infinite. And in this case, K here acts the same as tau. That is basically your time shift or time lag. Now, one thing I need to mention is here we wanted to find the phase difference between signals, not time difference. And cross correlation gives you time difference between the two signals. But if I know omega of the signals, right, or 2 pi f, the frequency of the signals, if I multiply it by this time delay between the two signals, I can get what? I can get the phase difference between them. So that is what you can do. So how would you do? How would you use cross correlation to calculate the phase difference between the two signals? Well, you just calculate Rxy of tau for different tau values, and then find the tau that maximizes this function. You multiply it by omega of the signals, or 2 pi f. F is in hertz, and that is going to give you the phase difference. Now, two things before we look at the MATLAB code about this method is, if the signals are noisy, cross correlation will not be an amazing tool, and it's not going to have a clear maximum. Okay? So before you use cross correlation on noisy signals, you might want to first do some filtering and remove high frequency signal, smoothing the signals before you apply cross correlation so you can get a clear maximum. The other thing is, if the signals have multiple periodic components, several frequencies in them, and several peaks, then in your cross correlation, you might also get several peaks as well. So now you need to do some extra analysis to determine which one of them is the dominant for the dominant frequency, okay, which one of those time delays or the phase shifts. So in this case, in this MATLAB code, my signals are not noisy, they are clean, and they only have one frequency of pi over 6 in them, so cross correlation should do its job. But if I add noise or if I add several harmonics, it's not going to be as clean. As I said, when there is noise in the signal, it's better to use Hilbert transform method. But here, you see a similar thing is done, so I pass x1 and x2 to the xcore command, which does the normalized cross correlation, and it gives me different lags and different correlations. So these are taus, these are Rxy of tau. And once I have them, I look into the maximum of them, and once I find the index for the maximum, I read the tau for that maximum location, and that is just an index. So I need to multiply it by the time difference between this first and the second time point to get basically multiplied by dt to convert those indices into a real lag time, and then multiplied by 2 pi f to convert it into the shift. And then I can show that to you by converting it to degrees. And you see when I ran it, it calculated the value for me as 28.8 degrees. So although the signals were clean, no noise, no several harmonics, still this method calculated the phase lag as 28.8 degrees, while the Hilbert method did 30.02 degrees, and the actual one is 30 degrees. So you see that Hilbert does a better job. And feel free to change this, like change it to 60 degrees now, and run it again and look at the result. You see again, look, 60.02 degrees. Look how small the error is, but this one is 57.65 degrees. Okay, so in general, although both methods work, the Hilbert method does do a better job for finding phase difference between two signals. Hopefully this video was useful to you. I'm going to share this MATLAB code with you. You can download it under video description, and you can look at each one of these two methods. Thank you so much. I'll see you in the next lecture.